All right, in this video, we're going to be talking about complex roots. And before we get into that, I would like to reinforce the concept of a complex conjugate. Now, remember in the previous video, I spoke about the conjugate of a complex number being essentially the same complex number, but you replace the sign or you change the sign of the imaginary part. Now, a conjugate pair of complex numbers is a pair of complex numbers where the only difference is the sign of the imaginary part. Now, I have some scenarios, x plus yi and x minus yi. Are they conjugate pairs? And this is true. They are conjugate pairs because the only difference is the sign of the imaginary part, right? Now, what about the next one? 5i plus 3 and 3 minus 5i. Are they conjugate pairs? Yes, they are. They're conjugate pairs because the sign of the imaginary part is the only difference. What about the third one? Are these conjugate pairs? No, they're not. They're not conjugate pairs because the sign of the imaginary part is the same. What is really a root? Right? When you hear the term the roots of a quadratic equation, what do you think that means? Now, the roots of a quadratic equation are simply the x-intercepts. Right? They're the x-intercepts for that quadratic graph. And we find those x-intercepts by evaluating x when the quadratic equation is equal to 0. Right? Now, with some quadratic equations, like this one, they never cut the x-axis. So they don't have any real roots because they never cut that x-axis. They have no real x-intercepts, right? And if they have no real x-intercepts, what kind of x-intercepts are they going to have? They're going to have x-intercepts that are complex in nature. I'm going to show you an example of a quadratic graph with real x-intercepts and one with complex ones. All right, now looking at this graph, you can see that the x-intercepts are 2 and 3, right? So I have two roots, two real roots, right? That being 2 and another one being 3, right? Now, with another quadratic graph, let's say x squared plus x plus 1, that does not cut the x-axis. This has complex roots, right? Essentially, this graph is cutting the x-axis, but not in this dimension, right? Not in the real number system. And it kind of sounds crazy, but that's what's happening. Yeah. A quadratic equation with a discriminant value that is less than 0 has roots that are complex conjugate pairs. Now, first of all, what is the discriminant value? The discriminant value, in that quadratic formula, under that square root sign, there's this thing b squared minus 4a times c. Now, this is what we call a discriminant, and it gives us various characteristics about the quadratic function, right? If b squared minus 4ac, when we evaluate this, if it's less than 0, then our quadratic function never cuts the x-axis. If it's greater than 0, then we have two real distinct roots, right? The quadratic function cuts the x-axis at 2 points. Now, if b squared minus 4ac is equal to 0, then the quadratic function merely touches the x-axis. It cuts it once, right? Well, not really cuts it, but it kind of touches it, right? Now, going back to this equation, we got to find the roots. We're going to use a quadratic formula. x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, right? This is the discriminant, remember. X is equal to minus b, right? B is going to be 1, so minus 1 plus or minus the square root of b squared, 1 squared minus 4 times 1 times 1, all over 2 times 1. So x is equal to negative 1 plus or minus the square root of 1 squared minus 4, it's the same as 1 minus 4, which is minus 3, all over 2. X is equal to minus 1 plus or minus the square root of negative 3. The root of negative 3 can be expressed as the root 3 times the root of minus 1. All right, remember laws of indices. So it's going to be the root 3 times the root of minus 1, which is I. So I get plus or minus root 3i all over 2. So x could be minus a half plus root of 3 over 2i, or it could be minus a half minus the root of 3 over 2i. And these are complex conjugate pairs. All right? Now, if a quadratic equation has a discriminant value that is less than 0, the roots are complex conjugate pairs. If the discriminant value is greater than 0, then we have two real distinct roots. The graph cuts the x-axis at 2 points. If the discriminant value is equal to 0, then the graph merely touches the x-axis at 1 point. All right. Now let's talk about the relationship between the roots and coefficients of quadratic equations. Now, like I said earlier, roots are the x-intercepts, right? And we may find the roots of a quadratic equation by what? Equating to 0, then factorizing or using the quadratic formula, or maybe by computing the square or some other method. But with this example here, I am going to use the AC method, right? So A is 1, B is minus 5, C is 6. AC is going to be 6. Two numbers that multiply together is equal to 6, but when added together is equal to minus 5. It's going to be minus 3 and minus 2. Right? So I'm going to replace minus 5x with minus 3x minus 2x plus 6. Now I'm going to group these two together, factor out x into x minus 3, and I'm now going to factor out minus 2 into x minus 3. Right? I can now factor out x minus 3, so I have x minus 3 into x minus 2. Now, I took this here and I factorized it. So I can say that x squared minus 5x plus 6 is equal to x minus 3 all times x minus 2. And what is the significance of this 3 and this 2? That 3 and that 2, they're the roots, right? Look, I have a plot of the same graph. And you can clearly see that the x-intercepts would be 2 and 3. So let's say I have a quadratic equation. Ax squared plus bx plus c is equal to 0. I divide short by a, so I have x squared plus b over ax plus c over a is equal to 0 over a, which is 0. And I said that this quadratic equation has two roots. Let one root be alpha and the other one be beta. I can now say, using this idea up here, that x squared plus b over a, x plus c over a is equal to x minus alpha times x minus beta, right? And x squared plus b over a, x plus c over a is equal to, when I expand over here, I'll get x squared minus into alpha plus beta, x plus alpha beta. All right, I'm just skipping all the steps in the interest of time, but this is what I'm going to end up with. Now, if I compare the left-hand side with what's on the right-hand side, I can see that the coefficient of x is going to be b over a is equal to minus the sum of alpha and beta, right? So therefore, alpha plus beta is equal to minus b over a, right? And alpha times beta is going to be c over a. You see I have here x squared minus the sum of the roots plus the product of the roots, right? So x squared minus the sum of the roots, x plus the product of the roots. The coefficient of x is always minus the sum of the roots. All right, now we have this question. One root of a real quadratic equation is 2 minus 3i. And they want you to find the quadratic equation. Now, a real quadratic equation is simply one that has real coefficients, right? So, example, x squared plus 3x plus 2 is a real quadratic equation because it has a real coefficients. But a quadratic equation like, let's say, x squared plus ix plus 2 minus 3i is a complex quadratic equation because you have what? Non-real coefficients, right? Okay. Now, they said that one of the roots is 2 minus 3i. That's a complex number. Now, complex roots, they never occur by themselves. If one root is complex, then the other one is the complex conjugate, right? They always travel together. Never will you find a complex root being on its own. It's always going to have its conjugate partner. So if one of the roots is 2 minus 3i, then the other root is obviously going to be 2 plus 3i. So we already have both roots. So I'm going to use the fact that the coefficient of x is minus the sum of the roots, and the constant will be the product of the roots. All right? My quadratic equation will be found like this. X squared minus the sum of the roots minus the sum of alpha and beta. So minus into 2 minus 3i plus 2 plus 3i as the coefficient of x. Plus the product of the roots, right? 2 minus 3i times 2 plus 3i. All right. I now simplify. Minus 3i plus 3i can cancel out. 2 plus 2 is 4. So I essentially just have minus 4x here. Plus 2 times 2 is 4. Minus 3i times 3i is minus 9i squared. 2 times 3i is positive 6i. And minus 3i by 2 is minus 6i. So I see that this 6i's can cancel out. And I'm left with 4 minus I squared is minus 1. So I'm going to have 9 times minus 1. So that's going to be 4 plus 9, which is going to be 13. So I'm going to have x squared minus 4x plus 13 is equal to 0. This is the quadratic equation that has roots 2 minus 3i and 2 plus 3i. That's why it's important to understand the relationship between the roots and the coefficients of the quadratic equations.